So now for something very different. Chapter 11, liquids, solids, and intermolecular forces. Okay, so here is another video. This is like video day.
Dripping wet without gravity, and you wring it out, what's going to happen? What will happen to a wrung out cloth? So, and I had to use equipment that was here on board the space station. We might have the coolest washcloths ever here on the space station. I'm going to show you. Here's one of our washcloths. And it's packed in. It's put down into this little tiny hockey puck so that it saves space. But when you open up a hockey puck, and you pull out your washcloth. This is the one I'm going to use for the experiment today. And so when you open up your hockey puck and turn it into a washcloth, it was compressed in a great big vise somewhere. Okay, so here's my washcloth, like a magic trick. And now I'm going to get this soaking wet, and then we're going to see what will happen when we wring it out. Merit and Kendra suggested that I dip this in a bag, but bags don't hold water in space, so instead I filled a water bag. This has drinking water in it. And I'm going to squirt a bunch of water into this washcloth.
Microphones.
Okay, so here's a soaking wet washcloth. Get the microphone so you can hear me while I'm talking. And now let's start wringing it out. It's really wet.
Is that crazy? All over his hand.
The water's all over my hands. In fact, it rings out of the cloth into my hands. And if I let go of the cloth carefully, the water sort of doesn't stick to my hand. Okay, so the experiment worked beautifully. And the answer to the question is the water squeezes out of the cloth, and then because of the surface tension of the water, it actually runs along the surface of the cloth and then up into my hand, almost like you had Jell-O on your hands or gel on your hand, and it'll just stay there. Wonderful moisturizer in my hands. And the cloth doesn't really unravel itself. It just stays there floating like a dog's chew toy, soaking wet. Great experiment, worked perfectly. Meredith and Kendra, congratulations, great idea.
Isn't that cool? See if I can get this working again. Okay, so this is a still picture of that same guy. Looking at this large drop of water, right? And here we see a drop of water, and we see it sticking to the hand. So one of the things we're going to talk about in this chapter is how does water do that, right? Why does water do that? Intermolecular forces is how water can do that. These are forces of attraction between molecules. So the prefix inter means between molecules. Attractive forces, intermolecular forces, exist between all molecules and atoms. They are significant only at short distances, so the two atoms or molecules have to be very close together for it to be important at all. Intermolecular forces are the reason we have liquids and solids at all. If there were no intermolecular forces, all the atoms and molecules would just be individual gas particles. These forces are also essential for physiological processes. So the state of a sample of matter is going to depend on the strength of the intermolecular forces relative to the amount of thermal energy. So if you have high thermal energy, you've got a lot of movement of the particles, they're going to be able to break away from the intermolecular forces. I think of intermolecular forces as being a lot like Velcro, right? You can have really strong Velcro, and then it's going to take a lot of energy to separate the two pieces of Velcro. Or you can have very weak Velcro or a very small amount of Velcro, and you can pull those apart and you almost don't even notice it. So the strength of intermolecular forces varies, and how strong that is relative to the amount of thermal energy, the temperature, determines whether it's a solid, liquid, or a gas at that temperature.